Before we talk about reflection specifically, I want to talk a little bit more about the laser because I think it'll be helpful. So if you had to describe laser light, how would you describe it? Well, hopefully you would say that laser light is concentrated, right? We saw that normally if I have like a flashlight here, right? That light is not very concentrated. It's concentrated a little bit, but it does spread out a bit from the source. Normally a light bulb spreads out in all directions, but laser light's really concentrated. I would say rather than concentrated, I would say it's really intense and focused would be the more proper words to use. The other thing about laser light is always going to be one color because of the way that it is created. And a fancy name for one color is monochromatic, meaning one color. Very easy there. Normally, when we encounter light, most sources of light that we encounter are white light. So what's white light? White light actually is composed of the entire visible spectrum. Okay. Now it might be missing a frequency here or there depending on the source, but really it's just all of the colors of the visible spectrum overlapping. And what that does is it creates, when your brain, your eye gets white light, it's actually a lot of information because it's all those different colors. So the cones in your eye, all the parts of it are stimulated and your brain just kind of goes, freaks out and says, white, right? That's what white light is. It's actually visual noise. And that's the way our brain perceives it, and it can't parse one thing out from the other, and so we see that as white. So another more scientific way of saying it is that white light is polychromatic, right? Meaning it is many colors. But laser light is intense for a very particular reason, and it's not due just to monochromatic. Well, polychromatic light is never going to be as intense as monochromatic light because the interference that's going to happen with the polychromatic light, it's going to be layers upon layers and layers of different frequencies, different wavelengths that overlap, such that some of them will create constructive interference, some will create destructive interference. With monochromatic, that means that all of the light has the same wavelength. But just because it has, well, actually, hold on a second. Let me just draw what a polychromatic light would look like, okay? So if all of those frequencies overlapped, that's polychromatic. Now, I can have monochromatic light, meaning everything has the same wavelength. There you go. But those wavelengths could be out of phase with each other, and therefore you're not really getting all that much. So this is monochromatic, but out of phase. Okay, monochromatic, out of phase. All the same wavelength, but not overlapping. If I have monochromatic light that's entirely or completely in phase, that light wave would look like this. I'm not drawing them overlapping just to create a nicer picture there, right? Such that everything would line up and I would get a lot of constructive interference. This is what laser light looks like. There's a name for this. When you have monochromatic light where all the waves are completely in phase, it's called coherent light. A laser is coherent light. And that's why it is so intense, because not only is there no interference because the wavelengths are all the same, but you line up all the crests and all the troughs such that you get constructive interference, and that's what gives it that intense and focused flavor. Now, by the way, the word laser itself, I wrote it all in caps. That's because it's an acronym. It means light amplification by stimulated emission of radiation. So what's happening inside of a laser, I'm not going to go too much into it, but we have a gas enclosed in a tube, and that gas is being zapped with electricity. And when you zap certain gases with electricity in certain situations, you can get this coherent light. The laser I showed you, the red light, was a neon helium laser. So in the tube was a certain mixture of neon and helium. You can actually have different color lasers. For example, if you take xenon and you zap that, xenon gives you a purplish laser. If you take krypton and zap that, you get a green laser, right? You'll notice that all the gases that I'm using to create my laser are all what? And hopefully you said inert gases, right? They are the noble gases. We tend to use the noble gases in order to make lasers. So I just wanted to talk about lasers versus white light. Now, what we definitely saw in the last video was if this was my plane mirror, and if I had that coherent beam of light coming down to that, so that's the incident ray, that if I draw a normal line at the point that that ray intercepted, and I measure this, boom, oh, it's a 40-degree angle, that I got exactly a 40-degree angle on the other side, boom, that the law of reflection was clearly working for my laser light. So that's super important. And so this object here was a plane mirror, and I will tell you that the type of reflection that we're getting at a plane mirror is a hard reflection, meaning that it is the light is reflected and most of the energy is reflected back. Some of it is absorbed at the surface. That's why you could see the laser light actually bouncing off of it. If the laser light didn't actually, if it 100% reflected, we wouldn't have seen the dot of the laser light on the mirror itself. So let's talk then about reflection, because there's a lot going on there. For example, how come we see this as red? Well, what's happening there is, what sort of light is intersecting with this red pen cap? And that answer is white light coming from the lamp in my kitchen. So white light is hitting this, but apparently what's getting to my eye is red light. So what's happening? Oh, what's happening is, remember I said that the mechanism of seeing was there's got to be a source of light that interacts with an object and is oftentimes changed by that object and then gets to the retina of my eye. What this object is doing is absorbing all the frequencies of light except for what I'm seeing, and it's just reflecting back that one color. And that's what's happening when we see things, when we see colors, is that you have white light coming in, it hits the object absorbs all colors except what color you see. It also redirects the light, so it changes its direction, not only just changes what frequencies I'm seeing, and then that light gets to my eye. So it's sort of weird that this red pen cap, you know, it's actually just rejecting the red light. That's why I'm seeing it. So we'll talk in another video in just a moment about color theory, about what's going on there. But I just wanted to do one more thing about the law of reflection before we go on to color theory. So let's say I have a mirror, right? So here's a mirror, a plain mirror, like your bathroom mirror or like a full stand mirror. And I'm just going to draw the ground here. And I'm going to draw a person standing on the ground, right? So let's say, I don't know, there's this person's foot. This is terrible drawing, right? I only care about the foot, the head, and the eye, which is really kind of disturbing looking. It looks like the Richard Scarry, the inchworm kid, but there it is. So there's the eye. So I want to talk about how we see stuff with mirrors. Well, light from some source is hitting all the parts of the body and have to get to my eye, right? But what's happening here is that, so there are an infinite number of light rays that hit the shoe, right? I'm just gonna draw the one that gets to my eye, because I could draw an infinite number, but that's not helpful. And so what happens here is there is some light ray that bounces off the shoe, then gets to the mirror, and then I would have to find the exact angle, bum, 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 and then that gets to my eye. And I just ballparked it because I don't want to spend too much time making this perfect. But that's what happens there. Now, the question is, where does the brain perceive my shoe to be? Now, logically, we know the shoe is below us, but where the brain perceives the shoe to be is actually back this direction, okay? Because remember, the brain perceives that light travels in a straight line. Now, these two angles are not exactly equal. I should have found out where it would have to hit the mirror to get exactly equal, and I could do that geometry, but like, here's where we would see ourselves in this plane mirror. This here is called a virtual ray. It is where the brain perceives the light traveled from. And so how far back is this person behind the mirror? Well, if this angle has to equal that angle because of the law of reflection, then this angle has to equal that angle, right? Which means that this angle has to equal this angle. If those two angles are equal and these two sides are equal in these triangles, then these two distances have to be equal, right? We can kind of go through that if you want to do your side, angle, side. That's what I'm using here, angle, side, right? But the important thing here is that when you look in a plane mirror, the image that you're seeing seems to be just as far behind the mirror as you are in front of the mirror. And that should conform with your experience of working with plane mirrors, right? And just an application of the law of reflection. Now, if the mirror was curved, we'd have to go into a lot of different geometries because that would distort the image. Hopefully you've seen that before, how images can get distorted with concave or convex mirror. So if you have a concave mirror in your house, that's like a shaving mirror or a makeup mirror, take a look at that. What does that do to your image? Do you look as far behind it as you are in front of it? If you want to think about a convex mirror, that's actually the driver's side mirror as well as your rear view mirror, right? Think about what the image looks like there. Think about what's written on them. And those are just different ways that the images are distorted due to that geometry. But in the next video, we're going to talk about color theory and how that deals with reflection.